Hello, NATR 346. This is a quick video just on one of the problems in the land use and mixing module 7 problem set. I think that right now is taking the lead as the least popular problem set. A lot of people just skipped a lot of problems. That happens. That's okay. We'll get through this. There is a problem at the end, I guess number 6, toward the end, that a lot of folks just skipped. Some people asked about it for an explanation as to, what are you talking about? What do you want in this problem? What's up? And then after they found that out, they looked at it and still said, skip it. So I do want to go through this problem. It's, again, if you endeavored to try and you showed me some logic and reasoning, that's what I'm looking for. But I wanted to walk through what I was looking for on this problem as a kind of little teaching moment here, and trying to get some of these principles of water quality down. And I thought this was a good way to do that. So I want to walk through this and see what happens here. So in the problem, there are 6 sampling stations, A, B, C, D, E, F, and there are 7 results. Now these results are literally like when you go out and you put water meters in the river and you write down these parameters. That's what you would do. And it turns out you have 7 results, 7 times, and 6 stations, and the only thing you know is that the first result goes to station A. After that, it's scrambled. So what I was looking for here is the first thing to do is get rid of that extra data point. There's something wrong with one of these data points, and it's number 6. Number 6 has high dissolved oxygen. 6 parts per million is pretty high. Now, out of the tap, it's like 8. Water can hold up to 14 parts per million if it's darn near frozen, ice cold. And then as the temperature goes up, it can hold less and less. So kind of room temperature water, 6 to 8 ppm, that's good stuff. Got a lot of oxygen in it here. But it also has a lot of hydrogen sulfide and methane. And those are created when bacteria run out of oxygen and use other sulfate for an electron acceptor and make that rotten egg stink smell. So here we have stinky water with a lot of oxygen. Doesn't make sense. So there's just something wrong with number 6. So you throw that one out. First step. Now we'll start with our water at station A. Pretty good, low dissolved solids. This is pretty low. This is about what's in the delta. Again, there's a TDS 2-pager that talks about this stuff. Dissolved oxygen, high. Nitrate, this is kind of what you'd expect in the natural environment, maybe a little high, but it's pretty nice water. What do we expect from the ag watershed? We know from the eutrophication paper, and it's nitrate and phosphorus, nutrients. So what sample shows an increase in nitrate, but really nothing else? And that would be number 5. I would say 5 best fits here. We got a ton of nitrate coming in. It goes from 3 to 50. The DO stays the same. And TDS doubles because nitrate is a salt. So now we're at B and 5. Here's the water. It's got now kind of elevated TDS. Still good oxygen and a lot of nitrate. And then we go through this power of this cooling. So we're just going to raise the temperature of the water. That's the bottom line. We take then the water, it takes in some of this heat, and you discharge warmer water. That's all that happens. And for C then, I would go with 2 to go. So you're going from 5 at B to 2. The TDS doesn't change, 800 to 800. The nitrate doesn't go anywhere. All that happens is the temperature goes up, and so the dissolved oxygen goes from 7 to 3. That's just straight warming up of the water. So now at C, we're at 2. 800 TDS, a little dissolved oxygen, a lot of nitrate. Then we have a bunch of biological oxygen demand. A sewer should be sewer plant, not sewer plan. Overflow. Raw sewage into the river. Oops, it happens. A lot of biological oxygen demand. Now what you would expect, all the oxygen to go away, a lot of the nitrate to go away, as those bacteria start to use sulfate and methane to break down the organic matter. And so you should expect a bunch of little dissolved oxygen and a bunch of stinky byproducts. So where is that found? 7. The dissolved oxygen, we're going now from C, which is 2, to D, which is 7. So the dissolved oxygen goes from 3 to less than 1. The nitrate gets all used up. Remember, the bacteria use oxygen first, then they use nitrate, then they use sulfate and carbon and make these nasties. So D would be 7. Dissolved oxygen is gone, and we have these nasty byproducts, the stinky stuff, methane and hydrogen sulfide and the sulfide compounds as a result of the sewer overflow. Then we have rapids, which is just basically what you've learned we do at sewer plants, is just get oxygen back in that water so the bacteria that we like grow and eat up the biological matter. So what happens? How do you go from D? You're just going to aerate it. And so I think the best fit for E is number 3. So we're going from D7 to E3. The TDS stays the same. You're going through these rapids, you're just aerating the water. There's nothing happens to the salts. Now the dissolved oxygen starts to recover. You go from less than 1 to up to 3. I'm sorry, up to 5, E3. Nitrate is still gone. And now your methane and sulfide gets kind of worked out of the water down to these 2 and 1 levels. So now you're at E3. Now here you're just diluting this stream. You're just taking snowmelt, pure water with very low salts, very low, almost nothing but water in it. And you're diluting the flow at E. And E was number 3, so the best fit there is 4. Now finally the TDS goes down from 1,000 to 500. Where did the salt go? It's all still here, it's just diluted. That was also a key part of one of the problem sets, is that even if you decrease or increase the concentration, you may have the same amount of flux and flow. So you got a lot of TDS at E. It comes through here. The concentration goes down, but you have the same amount of salt. But anyway, so we're going from E3 to C4, E3 to C4. The TDS goes down because you added some you diluted it. Dissolved oxygen goes up because of cold water, cools it down. Nitrate, still no nitrate. The methane and the remaining hydrogen sulfide go away. So that's what I was looking for, but if you reasoned otherwise, if you would have said, I think some people did say, hey, there's nutrients coming in from the ag watershed, that's going to make algae. The algae is going to bloom and die, and the decaying algae is going to use up oxygen. And then you did something like having number 7 here because of that reasoning. That's fine. That could happen. That's a good point. Full credit. You'll have trouble kind of fitting the rest of them together, but it's, again, the logic. What do you expect to happen with water quality that I'm really looking for? Again, I hope that helps.